This video is walking through the understanding quadratic function activity. Before this, you should have gone through the example that looked at what makes a quadratic function quadratic. And through that, you would have discovered that a quadratic function ends up having a constant second difference. And that second difference is actually the rate of change of the rate of change. And so we're going to be looking today at what do the sort of A, B, and C sort of parameters of our quadratic function actually represent within context. And we'll be using sort of our ideas and what we know about functions in general and rates of change to gain a better understanding of what those sort of pieces of our function represent. And these ideas will actually sort of come back indirectly as you take future math courses. All right, so we're going to be looking at a function that models the population of Arizona. And so we were given a function, an equation this time, and we're also given a table of values. And so T is number of years since 2000, and P is the population of Arizona. And so question one is just, generally, how is the population changing? And, if we take a quick look here, I'll notice I start at, 5,112,000, and then it goes up to 5,369,000. And so each of these numbers is getting bigger. And so generally, the population is increasing. My graph is going up. Now, the next step is, the next question is asking, what is the population of Arizona in the year 2000? And that's right here in our table. The year 2000 would be our initial value. And so we have 5,112.35 thousand people. Now, if we take a look, this particular number does make an appearance in the equation. And so this value right here, notice it's the same as that number in our function. And so this is in that C position right there. And so this is our sort of C value. Now, why will C always come out as our vertical intercept? Well, if you remember, your vertical intercept should occur when your input value is 0. So in this particular case, or in any, if I want to sort of generalize this, if I took that sort of general quadratic function form and I replaced each of my variables with 0, I would have 0 squared plus b times 0 plus c. Both the the initial term, the squared term, and the x term would go away, and I'd be left with just c. And so on our quadratic function, that vertical intercept is always going to have a value of c. So we've sort of figured out what that c parameter represents. It's our initial value. All right, so let's turn our attention now to another parameter. So here we actually are going to want to estimate the instantaneous rate of change at the vertical intercept. So basically, we want to figure out the slope at sort of our initial point, as close as we can get. Now, normally a slope on a quadratic, here's sort of a quadratic, would be sort of, the rate of, average rate of change would get us sort of the slope between 2 points. But we want as close as we can to the slope sort of at an individual point, or what we'll call in calculus the slope of the tangent line. And so to do that, basically, our slope, or our rate of change would be the change in P over change in T, change in time. But we're going to want to make that change in time really, really small. And the smaller we can get, the smaller that interval is going to be, the closer we're going to get to the, instantaneous rate of change. Now, in the end, it's going to be an estimate, but we can sort of shrink that interval down as close as we can to get an accurate sort of an accurate estimate. And so I'm going to change for a minute over to Desmos. And so what you'll notice I've done here is I've put in our function, so that's up there, and I called it P, and then I created sort of a formula for the slope. Now I put in the letter A, and just to have you sort of look, so if we found the slope between 1 year, so 2001 and 2000, we would get 129.7 people per year. But I can make that interval a little smaller, so let's say we go to about 0.9, now we're up to 129.7 people per year. And so we can sort of keep shrinking this, but you might be going, well, why don't we shrink it to 0? But if you shrink it to 0, then I get a number over 0 and I can't divide by 0. So we want to get to as close to 0 without actually hitting 0. So notice now I'm at 0.02, so I'm getting a little closer. I'm actually going to switch to typing. 130.67 when I have, a hundredth as my difference. But what if I make it a little smaller? Now I'm at 130.679, or I could even make it smaller. And I can sort of see now as I make my number small, my sort of interval smaller and smaller. So this is the sort of the change in t interval right here. That's what A is representing. I can sort of start to see that it's going to round to 130.68, thousand people per year. Now, if I go back up to my quadratic function up top, and let's sort of close that out, you should notice, and I'm going to switch colors here, that shows up right here. That's my B value. So this number that we found, that instantaneous rate of change, is the B term of our quadratic function. And so what is the meaning of that parameter? Well, it's what we found here. It's the instantaneous. So it's if we could find the rate of change at that exact moment in time. So it's the instantaneous rate of change at the input value when the input value is 0. So in this particular situation, it is how quickly the population of Arizona was increasing in the year 2000. Exactly when it started. All right, so we've figured out what C represents. We've figured out what B represents. So now we're left to sort of figure out what this A value is. So, thinking we're going to want to sort of figure out, where does this negative 0.98 come from? Now, to do that, we're going to have to go sort of back to this idea of the rate of the rate. Now, looking here, you should notice we have the table here, and we're going to start by just finding the rate of change. Now, it is a change in P over change in T, and in this case, unlike one of our earlier examples, we actually need to find the average rate of change, because if you notice here, my change in T is 2. So it's not just going to be our change in Y, we need to divide out that change in time. So, it's going up by 2 every time. So plus 2, plus 2. And so what that means here is I would take the difference in my y's, so 5,369.79 minus 5,102.35, all divided by 2, and I would come out with 128.72, thousand people per year, and I'm running out of space. And I would keep doing this for all of them. And so this comes out to 124.8 and 120.88. And I noticed that this rate of change, this average rate of change, is getting smaller and smaller, but it is positive. And remember, initially we said that our function was increasing. And so that makes sense. Like, oh, it's a positive value. My function is, it's a positive slope. It's a positive rate of change. My function's going up. Now, the second rate sort of tells how the rate is changing. And I might notice just by looking that these numbers are getting smaller. So I sort of know in the back of my head that my rate is changing at a decreasing rate. So I'm going to expect these values to be negative. Now, notice I'm looking for the rate of change, which means I have that change in time again. So this is my change in the rate, and then divided by the change in time, which is still 2. And so here it'd be like the difference between these two. So 124.8 minus 128.72, all divided by 2, comes out to negative 1.96 thousands of people per year. I know, it's a weird unit. Or you could think of, thousands of people per year squared is another way sometimes people write it. I like the per year. And if I did this every single time, this is a quadratic function, so guess what's going to happen with my second difference? It ends up being the same. They're all negative, and that makes sense because remember we said it appeared to be a decreasing rate as we sort of went through. And so let's just interpret these numbers and sort of what they represent. So what is the rate of change from 2 to 4 mean in the context of the problem? Well, the population of Arizona increases at an average rate of, and then we're looking at this value right here, 124.8 thousand people per year between, and you have to give the years because the rate's not constant, 2002 and 2004. All right. So we completed the second tile. Describe what this information tells us. Well, as we mentioned earlier, the rate is decreasing at a constant rate. So the rate is decreasing at a constant rate of 1.96 thousand people per year every year. So every year that goes by, the rate decreases by that much. So let's go now to our function. Our question is, when we look at sort of this a value here, how does that a value relate to this 1.9, this negative 1.96? And this is a hard one to sort of see, but if you notice, to get from this value to that rate of the rate, this would be a multiply by 2 relationship. 0.98 times 2 would be 1.96.
Okay, this next problem asks us to recall the global iPad shipment example from the presentation. This presentation you should have worked through before beginning this quadratic activity. And we remember that the rate at which the rate was changing for that situation was this 2.66 million units per year each year. And then if we also remember the function for that situation was given by this formula here of S at t is 1.33 t squared minus 12.73 t plus 72.77. And so the question says, how does this rate of the rate, how does that compare with the A value in the global iPad shipment model? So the A value is this particular piece right here of the formula. Not a good color to use, so I'll just come back and circle it. The 1.33. So A is equal to 1.33. And we see that the rate at which the rate was changing is 2.66. And so the comparison, how do they compare? Well, I see that if I were just to take the 1.33 and multiply by 2, I would get 2.66. So what conjecture can I make? What does the A tell me? I know that if I take the A and double it, so 2A is the rate at which the rate is changing. So we saw that in our Arizona population problem, and we saw it in our iPad shipment problem, and we're making the conjecture that that will be the case, and indeed with the quadratic function, 2a, or the value of a doubled, is always the rate at which the rate is changing, and that's a constant value.
So if we want to summarize, we can kind of do that here. So the C value is always going to tell us the output in general of the vertical intercept. The B value is always going to tell us the instantaneous rate of change at my input is 0. And then 2A is going to tell us the rate at which the rate is changing. Now, all those things are well and good, but if we want to put this into context, so let's go back to our population example. So we know we have this. So one thing I could ask you to do is I could give you this problem just with this formula, and I could say, explain the meaning of A, B, and C. Generally, we start with C, and then we do B, and then we do A. So the first thing I would say is in the year 2000, so in 2000, the population of Arizona was 5112.35 thousand people. So that's my C value. So that tells me about this. But that population of 5,112,000 people, so that number was initially increasing by 130.68 thousand people per year. So that's not the rate of change over the entire year 2000. That was just the rate of change right when we knew the population was the 5112.35. So that's B. So here's C, here's B. So then what A is telling me, so we know that my rate of change is 0 was 130.68 thousand, but A is now telling me that the rate is decreasing at a constant rate of, 1.96 thousand people per year, every year. So you really need to have both, because this is really the units on the 1.96, the negative 1.96, and then that rate is changing every single year. So again, if we kind of summarize, this is again going back to this idea of rate of change, right? So C is telling us just an output value, B is telling us how that output value of C is changing, and then A is telling us how the rate is changing. So again, we start with C, B tells us about how C is changing, and then A tells us about how B is changing. So notice that we never use just A, we always use 2A.
So continuing on through this activity, we're going to look and see problem number 9 says models change based on the data used to generate the model. Okay, so for example, the population of Arizona in thousands, based on data from 2008 to 2020, can be modeled by the following function. And so here we're getting a completely different model for the population of Arizona than we were working with. And that's because this is based on different data. And in this case, the T is the number of years since 2010. So now we're being asked to explain the meaning of the parameters A, B, and C in the function g of t in the problem context. So let's go ahead and start with the C value. And so C is always the easiest one to start with. So the C value tells us that the population of Arizona in 2010, because when the T is equal to 0, that's 2010, was 6,405.15 thousand people. And this is according to the model, right? According to the model, that is the case. All right, so we have that one. Let's go ahead then and look at the B. What is the B parameter telling us? And B, we remember, is the instantaneous rate of change when T is equal to 0. So I would say then that this number right here, this population, so that number, or that value, was initially, so right at the moment that that value was recorded, it was initially increasing by 68.84 thousand people per year. So this tells us how the population of Arizona was increasing right at that moment of when T is equal to 0. And then the A coordinate, the A parameter tells us that the rate of change in the population is increasing at a constant rate of, it's going to be 3.29 times 2, and 3.29 times 2 is 6.58. So at a constant rate of 6.58 thousand people per year each year, because remember, this is the rate of the rate. So the rate was this initially was 68.84 thousand people per year, but that number was changing at a rate of 6.58 thousand people per year each year. And so we need to make sure we get all of the parts of that in there. And so then it goes on to say, explain the graphical meaning of these parameters. And so graphically, let me just change my pen for this one so it looks a little different on the screen here. Graphically, I would say that C is the output of the vertical intercept. So it is the value of the function when the input is 0. B is the instantaneous the instantaneous rate of change, at that vertical intercept. And then A is, A tells us that 2A, double A, is the constant rate of change of the rate of change. Or we could say the constant rate of change of the rate.